Every morning for the past 4.6 billion years, our star has risen with the mechanical precision of cosmic clockwork, bathing Earth in the golden light that powers photosynthesis, drives weather patterns, and makes possible every breath you've ever taken. The Sun appears in our sky as the very definition of permanence, a blazing disk of nuclear fire so constant, so reliable, that human civilizations have worshipped it as an eternal god, the unchanging source of all life and energy. But this perception of permanence is a cruel illusion, born of the brevity of human timescales. In the span of a single human lifetime, our Sun appears utterly stable, varying its energy output by less than 0.1% over decades of careful measurement. Generations of astronomers have recorded its predictable 11-year sunspot cycles, tracked the gentle ebb and flow of its magnetic field, and marvelled at the precise balance of forces that has maintained its steady burning for longer than complex life has existed on Earth. To us, the Sun seems as eternal as physics itself, a constant against which all other changes can be measured. Yet beneath this facade of stability, our star is engaged in a relentless process of self-consumption that began the moment nuclear fusion first ignited in its core. Every second, the Sun converts 600 million tons of hydrogen into helium through the inexorable process of nuclear fusion, releasing energy equivalent to 100 billion hydrogen bombs and radiating this power into the vacuum of space. This is not a sustainable process. It is a countdown clock written in the language of atomic physics, ticking away toward an inevitable conclusion that will transform our solar system beyond recognition. The cruel mathematics of stellar evolution reveal a truth that challenges our deepest assumptions about the permanence of our cosmic environment. Our Sun has already consumed roughly half of the hydrogen fuel in its core. We are living not in the early dawn of solar history, but at the solar system's midday, with roughly 5 billion years remaining until our star begins its final, catastrophic transformation. In cosmic terms, we exist during the middle chapters of a story whose ending has been written in the fundamental laws of physics since the moment our solar system formed. But the timeline of solar death is far more complex and terrifying than a simple expiration date 5 billion years in the future. The Sun's demise will not be a gentle fading into darkness, but a violent metamorphosis that will render Earth uninhabitable long before the final stellar collapse. Even now, subtle changes are already underway that herald the beginning of the end for our world as we know it. Our Sun is steadily growing brighter. This is not a recent development or a temporary fluctuation, but an inexorable consequence of the nuclear burning process that powers our star. As hydrogen in the solar core is converted to helium, the core becomes denser and hotter, causing the fusion reactions to proceed at an ever-accelerating rate. The Sun today is approximately 10% brighter than it was when life first emerged on Earth 3.8 billion years ago, and this gradual brightening will continue to accelerate as the solar core evolves. This 10% increase might seem insignificant, but it represents an enormous change in the energy environment that governs Earth's climate. The delicate balance of atmospheric composition, ocean circulation, and ice coverage that has maintained liquid water on our planet's surface for billions of years is already under stress from this increased solar output. Climate scientists studying the long-term evolution of Earth's environment have calculated that our planet's oceans will begin to evaporate catastrophically within approximately 1 billion years, not from human-induced climate change, but from the inexorable brightening of our aging Sun. This timeline places Earth's ultimate habitability within a timeframe that is simultaneously unimaginably distant and disturbingly finite. 1 billion years represents roughly 200,000 times the entire span of human civilization, a period so vast that it encompasses the entire history of complex multicellular life on Earth. Yet in the context of our planet's 4.6 billion year history, it represents merely the final chapter of a story that began when Earth was still a molten ball of rock bombarded by asteroids and comets. The realization that our Sun is mortal forces us to confront the temporary nature of everything we consider permanent. Every mountain range that has ever thrust up from Earth's crust, every ocean that has ever harboured life, every continent that has drifted across our planet's surface has existed under the light of a star that is slowly but inevitably dying. The Himalayas, thrust skyward by the collision of continental plates over the past 50 million years, will be reduced to nothing more than atomic vapor long before our Sun completes its stellar evolution. The Atlantic Ocean, which began opening 200 million years ago when the supercontinent Pangaea broke apart, will be a memory boiled away into space billions of years before the final curtain falls on our solar system. But the death of our Sun will not be a simple matter of the lights going out. Stellar evolution follows a complex sequence of phases, each more dramatic and destructive than the last. As the hydrogen fuel in the solar core becomes depleted, our Sun will begin to fuse helium into heavier elements, a process that generates far more energy and causes the star to swell to enormous proportions. During this red giant phase, which will last for several 100 million years, our Sun will expand to perhaps 200 times its current diameter, potentially engulfing the orbits of Mercury, Venus, and possibly even Earth. The transformation from the familiar yellow dwarf star we know today into a bloated red giant will be one of the most dramatic events in the history of our solar system. The Sun's surface will cool from its current temperature of 5,800 Kelvin to perhaps 3,000 Kelvin, giving it the deep red colour that characterises these stellar monsters. But despite this surface cooling, the total energy output will increase dramatically, bathing the solar system in radiation that will vaporize any remaining atmospheres on the inner planets and turn the frozen moons of the outer solar system into temporary havens of liquid water. Even if Earth somehow survives physical engulfment by the expanding red giant, a possibility that depends on complex interactions between solar mass loss and planetary orbital evolution, our world will be transformed into a hellscape that makes Venus look hospitable by comparison. Temperatures will soar to thousands of degrees, hot enough to melt the surface rocks into oceans of lava. The atmosphere, if any remains, will be stripped away by the intense stellar winds that accompany the red giant phase. The magnetic field that has protected Earth from cosmic radiation for billions of years will be overwhelmed by the electromagnetic chaos of our dying star. But even this dramatic red giant phase represents merely the penultimate act in our Sun's stellar death throes. After exhausting its capacity to fuse helium into heavier elements, our Sun will undergo a series of violent pulsations that will expel its outer layers into space, creating one of those beautiful but haunting structures known as planetary nebulae. The core that remains will collapse into a white dwarf, a stellar remnant the size of Earth, but containing roughly half the mass of the current Sun, so dense that a teaspoon of its material would weigh several tons. This white dwarf remnant will continue to shine for trillions of years, gradually cooling from white hot to red to brown to black as it radiates away the last of its stored thermal energy. In its immediate aftermath, the white dwarf will be surrounded by a spectacular nebula composed of the expelled outer layers of the former Sun, illuminated by ultraviolet radiation from the hot stellar core. This phase, lasting perhaps 100,000 years, will create a cosmic light show visible from thousands of light years away, a beautiful funeral pyre for our solar system that will serve as a beacon, announcing the death of the star that once nurtured life on Earth. The implications of stellar death extend far beyond the mere termination of familiar astronomical objects. The death of our Sun represents the end of the only known cradle of consciousness in the universe, the termination of a 4.6 billion year experiment in planetary evolution that culminated in the emergence of intelligence capable of contemplating its own cosmic context. Every work of art ever created, every scientific discovery ever made, every act of love and compassion that has ever occurred has taken place under the light of a star that is destined to destroy the world that gave it birth. Yet perhaps the most unsettling aspect of stellar death is not its inevitability, but its pervasiveness throughout the cosmos. Our Sun is just one of roughly 400 billion stars in the Milky Way galaxy, and virtually every one of them is engaged in the same inexorable process of nuclear self-consumption. The night sky that appears so permanent and eternal to our eyes is actually a vast graveyard in slow motion, filled with stars in various stages of their journey toward death. Some are just beginning their fusion processes, destined to burn for trillions of years. Others are already swollen into red giants, consuming whatever worlds they once nurtured. Still others have already completed their stellar evolution, leaving behind white dwarfs, neutron stars, or black holes as monuments to their former glory. The beautiful Helix Nebula, visible through telescopes as the Eye of God, is actually the remains of a sun-like star that died roughly 10,000 years ago, its outer layers expelled into space to create a ghostly shell surrounding a white dwarf core. This cosmic symmetry represents a preview of our own solar system's fate, a glimpse across time and space of the destiny that awaits every star and every planet in the universe. When astronomers photograph such planetary nebulae, they are essentially taking portraits of our own future, capturing the moment when stellar death transforms destruction into beauty. Standing beneath our sun's familiar warmth, knowing what we now know about the timeline of stellar evolution creates a profound sense of cosmic vertigo. We exist during a brief, precious interval when our star provides the stable energy that makes complex life possible. This interval, roughly 10 billion years from the sun's formation to its expansion into a red giant, represents the entire window of opportunity for the emergence and evolution of consciousness in our solar system. We are living during the golden age of solar stability, a cosmological moment that will never be repeated once our star begins its final transformation. The ancient Greeks spoke of the Golden Age as a lost time of perfection and harmony that existed before the corruption of the world. In a cosmic sense, we are still living in that Golden Age, the age when our star burns with the perfect stability that allows worlds to harbour oceans, atmospheres, and life. But unlike the mythological Golden Age, ours comes with an expiration date written in the fundamental physics of stellar evolution. Every sunrise represents both a daily renewal of the light that makes life possible and a step closer to the final sunrise that will end the story of terrestrial evolution. The sun that rose this morning over mountains and oceans, over cities and wilderness, over the entire pageant of human civilization is minutely but measurably brighter than the sun that rose yesterday, and it will be brighter still tomorrow. This gradual brightening, imperceptible on human timescales but inexorable over cosmic time, represents the beginning of the end of the only world we have ever known. But long before our star dies, it will transform into something that will render Earth uninhabitable, beginning a sequence of events that will test the limits of what we understand about planetary survival in the face of stellar evolution. Deep within the Sun's core, 150 million kilometers beneath the surface that bathes Earth in life-giving light, nuclear furnaces burn at temperatures that dwarf anything in human experience. Here, compressed to densities 150 times greater than water and heated to 15 million degrees Celsius, hydrogen nuclei collide with such violence that they overcome the fundamental electromagnetic force that normally keeps atomic particles apart. In this realm of crushing pressure and unimaginable heat, 4 hydrogen nuclei fuse together to create a single helium nucleus, releasing energy equivalent to the explosion of 20 million tons of TNT. This is the proton-proton chain reaction, the nuclear process that has powered our Sun for 4.6 billion years and will continue to sustain it for roughly 5 billion more. Every second, 600 million tons of hydrogen vanish into 596 million tons of helium, with the missing 4 million tons converted directly into energy according to Einstein's famous equation E equals mc squared. This energy, created in the Sun's core, begins a journey that will take between 100,000 and 200,000 years to reach the surface, buffeted and absorbed countless times by the dense solar material before finally escaping as the sunlight that warms our faces. But this process of nuclear fusion, for all its awesome power and apparent stability, contains within it the seeds of the Sun's eventual destruction. The helium nuclei produced by hydrogen fusion are heavier than the hydrogen they replace, causing the solar core to gradually become denser and more compressed over geological time. As the core density increases, the temperature rises, accelerating the fusion reactions and causing our Sun to grow steadily brighter. The 10% increase in luminosity that has occurred since Earth's formation is just the beginning of a process that will accelerate dramatically over the coming billions of years. Current models of stellar evolution, refined through decades of observations of other Sun-like stars throughout the galaxy, reveal that our Sun's brightness will continue to increase at an accelerating pace. Within 1.1 billion years, solar luminosity will have increased by approximately 10% over current levels, enough to trigger a runaway greenhouse effect that will vaporize Earth's oceans and transform our world into a Venus-like hellscape. Within 3.5 billion years, the Sun will be nearly 40% brighter than it is today, creating surface temperatures on Earth that will exceed 1,000 degrees Celsius, hot enough to melt zinc and lead. But these gradual changes represent merely the prelude to the catastrophic transformations that will occur when our Sun exhausts the hydrogen fuel in its core. Unlike the controlled burn of hydrogen fusion that has characterized the Sun's main sequence lifetime, the transition to helium burning will be violent and chaotic, marked by dramatic instabilities that will fundamentally alter our star's structure and energy output. The sequence of events begins when approximately 12% of the Sun's original hydrogen has been converted to helium in the core, a threshold our star will reach in roughly 5 billion years. As the hydrogen fuel becomes depleted, the fusion reactions in the core will begin to slow, reducing the outward pressure that has balanced the Sun's own gravity for billions of years. The core will start to contract under its own weight, and as it shrinks, gravitational compression will cause its temperature to rise dramatically. This core contraction triggers the next phase of stellar evolution, hydrogen shell burning. While the core itself no longer supports fusion reactions, the increasing temperature caused by gravitational compression will ignite hydrogen fusion in a spherical shell surrounding the inert helium core. This shell burning produces more energy than the Sun's current core fusion, causing our star to expand and cool as the additional energy pushes the outer layers farther from the center. The Sun will begin its transformation into a red giant. This expansion will not occur gradually over billions of years, but relatively quickly on astronomical timescales. Within perhaps 100 million years, our Sun will swell to many times its current diameter. The surface temperature will drop from the current 5,800 Kelvin to roughly 3,500 Kelvin, giving the star the deep red color that characterizes these stellar monsters. But despite the cooler surface temperature, the total energy output will increase dramatically as the Sun's surface area expands exponentially. The red giant phase represents one of the most dramatic transformations possible for a star like our Sun. At its maximum extent, our star may expand to 200 times its current diameter, with a surface that extends beyond the current orbit of Earth. The gravitational effects alone will be catastrophic for the inner solar system, as the expanded solar atmosphere creates drag that will cause surviving planets to spiral inward toward the stellar core. Mercury will be the first victim, its orbit decaying rapidly as it plows through the outer layers of the red giant Sun. The planet will be vaporized entirely, its rocky material scattered through the solar atmosphere or accreted onto the stellar surface. Venus will follow shortly afterward, its thick carbon dioxide atmosphere offering no protection against the overwhelming heat and gravitational forces of the nearby stellar surface. Earth's fate during the red giant phase remains one of the most actively debated questions in stellar evolution. Computer models produce conflicting results depending on the precise assumptions about solar mass loss, atmospheric drag, and tidal interactions. Some simulations suggest that Earth will be engulfed and vaporized like Mercury and Venus, its rocky material joining the expanding stellar envelope. Other models indicate that our planet might survive physical engulfment, but at a cost that makes survival meaningless. Surface temperatures exceeding 1,500 degrees Celsius, complete atmospheric loss, and transformation into a molten ball of rock orbiting within the atmosphere of a red giant star. The most optimistic scenarios suggest that Earth might actually move to a higher orbit as the Sun loses mass during the red giant expansion, potentially escaping physical destruction. But even in these scenarios, the intense radiation from the nearby stellar surface would sterilize our planet completely, boiling away any remaining water and stripping away the atmosphere that has protected life for billions of years. As the red giant phase progresses, the inert helium core will continue to contract and heat up under the crushing weight of the stellar material above it. When the core temperature reaches approximately 100 million degrees Celsius, nearly 7 times hotter than the current solar core, a new type of nuclear fusion will suddenly ignite. Helium nuclei will begin fusing together in a process known as the triple alpha reaction, converting helium into carbon and oxygen while releasing enormous amounts of energy. The onset of helium fusion will trigger one of the most violent events in stellar evolution, the helium flash. Unlike the gradual ignition of hydrogen burning that occurred when our Sun first formed, helium fusion begins explosively, with the energy output increasing by a factor of billions within minutes. This helium flash will cause massive convective upheavals throughout the stellar interior, mixing material that has been stratified for billions of years and temporarily stabilizing the star's structure. Following the helium flash, our Sun will enter a new phase of equilibrium, burning both hydrogen in a shell around the core and helium in the core itself. This phase, known as the horizontal branch, will last for approximately 100 million years, a brief respite in the star's otherwise catastrophic evolution toward death. During this period, the Sun will be smaller and less luminous than during the initial red giant expansion, but still far larger and more energetic than the star we know today. But this stability is temporary. As the helium fuel in the core becomes depleted, our Sun will face the same crisis that triggered the red giant expansion: the cessation of fusion reactions in the stellar center and the renewed contraction of the core under gravitational compression. However, unlike hydrogen, which can be burned in shells surrounding the core, helium burning requires such extreme temperatures that it cannot be sustained in the cooler regions outside the core. The depletion of helium fuel will trigger a second red giant phase, even more extreme than the first. The Sun will expand to perhaps 300 times its current diameter, with surface temperatures dropping to as low as 2,500 Kelvin. The stellar winds during this phase will be so intense that our Sun may lose 30% or more of its total mass, expelling its outer layers into space at velocities of hundreds of kilometers per second. These stellar winds will carry with them the nuclear products of billions of years of fusion reactions, not just the helium created from hydrogen burning, but carbon and oxygen forged in the extreme temperatures of helium fusion. This material, enriched with heavy elements that did not exist when our Sun first formed, will be scattered throughout the local interstellar medium, eventually becoming incorporated into new generations of stars and planets. The violence of this second red giant phase will far exceed anything that occurred during the initial expansion. Massive convection cells will transport material from the deep interior to the stellar surface, while instabilities in the nuclear burning shells will cause dramatic fluctuations in luminosity. Our Sun may vary in brightness by factors of thousands over periods of just a few years, creating a chaotic radiation environment that would instantly sterilize any remaining life in the solar system. During the most extreme phases of this evolution, our Sun will experience thermal pulses, periodic episodes when the helium-burning shell becomes unstable and releases enormous bursts of energy. These pulses, occurring roughly every 100,000 years, will cause the star to brighten dramatically and expel massive amounts of material into space. Each pulse will strip away more of the Sun's outer envelope, gradually exposing the hot, dense core that has been hidden beneath layers of stellar atmosphere for billions of years. The end result of this process will be the complete ejection of the Sun's outer layers, leaving behind only the dense, hot core, a white dwarf star with roughly half the mass of the current Sun compressed into a sphere the size of Earth. The expelled material will form a planetary nebula, one of those beautiful, ghostly structures that astronomers observe throughout the galaxy as monuments to stellar death. But the formation of the white dwarf does not represent the end of our Sun's influence on the solar system. The dramatic mass loss during the red giant phases will fundamentally alter the gravitational architecture of the planets, causing orbital migrations that will reshape the entire outer solar system. The gas giants, Jupiter, Saturn, Uranus, and Neptune, will migrate outward as the Sun loses mass, carrying their complex systems of moons into new orbital configurations. Some of these moons, particularly those of Jupiter and Saturn that currently exist as frozen worlds in the outer darkness, may experience a brief renaissance during the white dwarf phase. The hot white dwarf, though much smaller than the current Sun, will initially radiate enormous amounts of energy due to its extreme surface temperature of 100,000 Kelvin or more. This intense radiation will create a new habitable zone much closer to the stellar remnant, perhaps where Mercury orbits today. Europa, Enceladus, Titan, and other icy moons that migrate inward with their parent planets may find themselves in this new habitable zone, their frozen surfaces warming for the first time in billions of years. Liquid water oceans may form on these worlds, creating the possibility for a second genesis of life in our solar system's dying days. But this renaissance will be brief. Within a few 100 million years, the white dwarf will cool sufficiently that even these temporarily warmed worlds will return to their frozen state. The white dwarf itself will continue to radiate energy for trillions of years, gradually cooling from white hot to yellow to red to brown as it exhausts its store of thermal energy. Unlike main sequence stars that generate energy through nuclear fusion, white dwarfs are simply cooling off. Massive, stellar cinders that will eventually fade to black as they reach thermal equilibrium with the cosmic background radiation. Throughout the galaxy, this same drama of stellar death is playing out on countless stages. The Ring Nebula in Lyra, the Cat's Eye Nebula in Draco, the Helix Nebula in Aquarius. All of these beautiful structures are the funeral pyres of sun-like stars, the glowing shrouds that mark the transformation from main sequence star to white dwarf. When we observe these planetary nebulae through our telescopes, we are looking both backward and forward in time, backward to the deaths of stars that expired thousands of years ago, and forward to the fate that awaits our own solar system. Recent observations with the Hubble Space Telescope and other advanced instruments have revealed planetary nebulae of extraordinary complexity and beauty, with intricate structures that speak to the violent and chaotic nature of stellar death. Some show multiple shells of expelled material, evidence of repeated episodes of mass loss during the final red giant phases. Others display jets and knots of material moving at high velocities, suggesting that magnetic fields and stellar rotation play important roles in shaping the death throes of stars. The Stingray Nebula, the youngest known planetary nebula, provides a real-time glimpse of stellar death in progress. Located 18,000 light-years from Earth, this structure has formed within the past few decades, allowing astronomers to watch the transformation from red giant to white dwarf as it unfolds. The central star, which was a red giant just 20 years ago, is now heating up as its outer layers are stripped away, ionizing the expelled material and causing it to glow with the characteristic colours of a planetary nebula. Such observations confirm the theoretical models of stellar evolution and provide sobering previews of our own sun's fate. The death of a star like our sun is not a gentle fading into darkness, but a violent and dramatic transformation that reshapes entire planetary systems and scatters the products of stellar nucleosynthesis throughout the galaxy. As our sun begins its final transformation, Earth will face trials that no planet in our solar system has ever survived. Temperatures that will melt rock, radiation that will strip away atmospheres, and gravitational chaos that will reshape the very architecture of the worlds we call home. In the scorching Atacama Desert of northern Chile, where rainfall is measured in millimeters per decade, and the landscape resembles the surface of Mars more than any earthly environment, scientists have discovered something that chills the soul, despite the blazing sun overhead. Here, in this most desolate corner of our planet, lie the mineralized remains of ancient microorganisms that once thrived in conditions so extreme they seemed impossible for life to endure. These fossils, preserved in salt deposits and volcanic glass, represent the last gasps of ecosystems that died not from sudden catastrophe, but from the slow, inexorable process of their world becoming uninhabitable. The Atacama serves as an eerie preview of Earth's distant future, a glimpse of what our entire planet will become as our sun grows steadily brighter and the delicate balance that maintains liquid water begins to collapse. But unlike the regional aridity that created the Atacama Desert, the transformation awaiting Earth will be global, irreversible, and far more complete than anything our planet has experienced in its 4.6 billion-year history. The process has already begun. Over the past 4 billion years, as our sun has steadily consumed hydrogen in its core and grown approximately 30% brighter, Earth has maintained its habitable climate through a remarkable regulatory system known as the carbonate-silicate cycle. This planetary thermostat works by removing carbon dioxide from the atmosphere during warm periods and releasing it during cool periods, maintaining global temperatures within the narrow range where liquid water can exist. When the planet warms, increased rainfall accelerates the weathering of silicate rocks, which absorbs atmospheric CO2. When it cools, reduced weathering allows CO2 levels to rise, creating a greenhouse effect that prevents runaway ice formation. This system has kept Earth habitable even as solar luminosity increased by nearly a third since life first emerged. But like all regulatory mechanisms, the carbonate-silicate cycle has limits, and current climate models indicate that our planet is approaching the point where this ancient thermostat will no longer be able to compensate for our sun's increasing brightness. The breakdown begins subtly, with changes so gradual they would be imperceptible to any civilization observing over mere millennia. As solar luminosity continues its inexorable increase, global temperatures will rise despite the carbonate-silicate cycle's attempts at regulation. The increased warmth will accelerate evaporation from the oceans, loading the atmosphere with ever greater quantities of water vapour. Unlike carbon dioxide, whose greenhouse effect can be modulated by geological processes, water vapour creates a positive feedback loop that amplifies warming rather than regulating it. Water vapour is an extraordinarily potent greenhouse gas. Molecule for molecule, it traps heat far more effectively than carbon dioxide. As more water evaporates into the atmosphere, it absorbs more infrared radiation from Earth's surface, causing additional warming that drives even more evaporation. This runaway greenhouse effect represents one of the most terrifying feedback loops in planetary science, a process that transforms stable, habitable worlds into hellish landscapes where temperatures soar beyond the boiling point of water. Climate scientists studying this process have identified the point of no return with disturbing precision. When atmospheric water vapour reaches a critical threshold, currently estimated at roughly 10% of total atmospheric mass, the runaway greenhouse effect becomes unstoppable. Earth's surface temperature will begin climbing rapidly toward equilibrium with incoming solar radiation, a process that will culminate in global surface temperatures exceeding 1,400 degrees Celsius. The oceans will boil away entirely, their water molecules photodissociated by ultraviolet radiation in the upper atmosphere, with the lightweight hydrogen escaping to space and leaving behind an increasingly dense atmosphere of oxygen, nitrogen, and trace gases. Current models suggest this catastrophic transition will occur within approximately 1 billion years, triggered by solar luminosity increases that will make our sun roughly 10% brighter than it is today. 1 billion years may seem like an unimaginably distant future, but in the context of Earth's history, it represents barely 1/5 of the time that has elapsed since our planet formed. Complex multicellular life has existed on Earth for only about 600 million years, meaning that the remaining time for biological evolution is less than twice the duration that life has had to develop from simple algae to the extraordinary diversity of organisms we see today. The transformation will not occur suddenly, but as a gradual acceleration of processes already visible in Earth's climate system. The first signs will appear in the behaviour of clouds, those ephemeral formations that currently help regulate planetary temperature by reflecting sunlight back to space. As surface temperatures rise and atmospheric moisture increases, cloud formation patterns will shift dramatically. Low-altitude clouds that currently provide cooling by reflecting solar radiation will be replaced by high-altitude water vapour that traps heat near the surface. The hydrological cycle, that fundamental process by which water evaporates from oceans, condenses into clouds, and returns to the surface as precipitation, will become increasingly unstable. Massive storm systems will develop as the atmosphere struggles to transport and release the enormous quantities of water vapour generated by accelerating evaporation. These superstorms will dwarf anything in recorded history, with wind speeds that could exceed 300 km per hour and precipitation rates measured in meters per hour rather than millimeters. But even these violent attempts to maintain hydrological equilibrium will prove futile as the runaway greenhouse effect takes hold. Eventually, surface temperatures will become so high that water can no longer condense into liquid droplets, regardless of atmospheric pressure. The familiar cycle of evaporation and precipitation that has shaped Earth's climate for billions of years will cease entirely, replaced by a permanent atmosphere of superheated steam that will make the surface uninhabitable for any form of life as we know it. The geological consequences of this transformation will be as dramatic as the atmospheric changes. As temperatures soar beyond the melting points of common minerals, Earth's crust will begin to soften and flow like viscous liquid. The tectonic processes that have shaped our planet's surface for billions of years, the collision of continental plates that builds mountain ranges, the seafloor spreading that opens new ocean basins, The volcanic activity that recycles carbon between the atmosphere and the interior will accelerate dramatically under the extreme heat. Massive volcanic eruptions will become commonplace as the softened crust loses its ability to contain the pressures building in Earth's interior. These eruptions will release enormous quantities of previously sequestered carbon dioxide, water vapor, and other greenhouse gases, further accelerating the runaway warming process. The familiar landscapes that have provided the stage for the entire drama of terrestrial evolution, the mountain ranges, river valleys, coastal plains, and oceanic basins, will be obliterated as the crust becomes plastic and flows under its own weight. The fate of Earth's magnetic field during this transformation remains uncertain, but the prospects are ominous. Our planet's magnetosphere is generated by the circulation of molten iron in the outer core, driven by convection patterns that depend on specific temperature and pressure gradients within the Earth's interior. The extreme heating of the surface and upper mantle may disrupt these convection patterns, potentially weakening or even eliminating the magnetic field that has protected our atmosphere from solar wind stripping for billions of years. Without magnetic protection, the superheated atmosphere will be vulnerable to erosion by charged particles from the solar wind. The same process that stripped away much of Mars' atmosphere over geological time will begin operating on Earth, gradually removing the water vapor and other gases that accumulated during the runaway greenhouse phase. Paradoxically, this atmospheric loss may eventually cool the planet's surface, but by then the damage will be irreversible. The oceans will be gone, the crust will have been resurfaced by volcanic activity, and any record of Earth's biological heritage will have been erased. Long before the runaway greenhouse effect reaches its catastrophic conclusion, the biosphere will begin experiencing a slow-motion mass extinction that will make the end Permian event look like a minor perturbation. The first casualties will be the photosynthetic organisms that form the base of virtually all terrestrial food webs. As temperatures rise and atmospheric composition changes, the delicate biochemistry of photosynthesis will be disrupted, causing widespread plant die-offs that will cascade through entire ecosystems. The process will begin in the most sensitive environments, coral reefs, alpine meadows, Arctic tundra, where organisms already exist at the margins of their thermal tolerance. But as global temperatures continue rising, even the most heat-tolerant plants will succumb to conditions that exceed the limits of carbon fixation and cellular metabolism. The great forests that currently absorb billions of tons of atmospheric carbon dioxide will become net sources of greenhouse gases as dead vegetation decomposes and releases its stored carbon back to the atmosphere. Marine ecosystems will face an equally grim fate as ocean temperatures rise and acidity increases. The gradual warming of seawater will reduce its capacity to hold dissolved oxygen, creating vast dead zones where complex life cannot survive. Marine plants and algae, which currently produce roughly half of Earth's atmospheric oxygen, will be eliminated by the combination of heat stress, acidification, and reduced light penetration through increasingly turbid water. The extinction will proceed from the bottom of the food web upward, as primary producers disappear and leave consumers without energy sources. Herbivores will starve as plant communities collapse, followed by the carnivores that depend on them. The complex ecological relationships that have evolved over hundreds of millions of years, pollination networks, predator-prey dynamics, symbiotic partnerships, will unravel as species are eliminated faster than new relationships can evolve. Even organisms that seem well adapted to extreme conditions will struggle to survive the rapid pace of environmental change. The extremophile bacteria that thrive around hydrothermal vents at temperatures exceeding 120 degrees Celsius represent some of the most heat-tolerant life forms on Earth. But even these hardy organisms have specific requirements for pressure, chemical composition, and energy sources that may not persist as Earth's surface environment becomes completely unrecognizable. The final survivors may be found in the deepest parts of the Earth's crust, where subsurface communities of microorganisms have existed for billions of years, deriving energy from radioactive decay and chemical reactions rather than solar radiation. These deep biosphere communities, recently discovered living several kilometers below the surface in environments completely isolated from the surface world, may represent the last redoubt of terrestrial life as the planet above becomes uninhabitable. But even these subterranean ecosystems will face eventual extinction as the extreme surface heating penetrates deeper into the Earth's crust. The temperature gradient that allows life to exist in the deep subsurface will be compressed and eventually eliminated as surface temperatures approach those of the underlying rock. The final chapter of Earth's biological story may be written in darkness, kilometers below a surface that has become more hostile to life than the vacuum of space. The timescale of this biological collapse will be measured not in the sudden catastrophic events that characterize previous mass extinctions, but in the gradual degradation of environmental conditions over millions of years. Unlike the asteroid impact that ended the Cretaceous period, or the volcanic eruptions that triggered the end Permian extinction, the solar-driven extinction will be a slow strangulation that allows no possibility of recovery or adaptation. As we contemplate this distant but inevitable future, we must confront the sobering reality that every aspect of the natural world we consider permanent and eternal is actually temporary, sustained only by the current balance of solar energy input and planetary regulatory mechanisms. The Amazon rainforest, the Great Barrier Reef, the polar ice caps, the seasonal migrations of animals across continents, all of these natural wonders exist within a narrow window of solar luminosity that is already closing. The fossil record that future galactic archaeologists might discover on our transformed planet will tell the story of a world that briefly flowered with an extraordinary diversity of life before succumbing to the inexorable brightening of its parent star. The geological layers will preserve evidence of forests turned to coal, reef systems calcified into limestone, and the remains of countless species that evolved, flourished, and vanished during Earth's brief moment as a garden world in an otherwise hostile cosmos. But these slow changes are merely the prelude to the catastrophic final act that awaits when our Sun exhausts its core hydrogen and begins the violent transformation that will reshape our entire solar system beyond recognition. 5 billion years from now, in the final moments before our Sun exhausts the hydrogen fuel in its core, the star that has nurtured life on Earth for geological ages will begin a transformation so violent and complete that it will erase every trace of the solar system we know. The change will not announce itself with fanfare or warning signs visible to any hypothetical observers. One day, the nuclear fusion reactions that have maintained stellar equilibrium for billions of years will simply begin to falter, and the delicate balance between gravitational collapse and radiation pressure that defines a main sequence star will start to fail. The core, now composed primarily of inert helium ash from eons of hydrogen burning, will no longer generate sufficient energy to support the immense weight of the stellar material above it. Gravity, that inexorable force that has waited patiently for this moment throughout the Sun's entire lifetime, will finally gain the upper hand. The core will begin to contract, and as it shrinks under its own weight, the temperature will soar to levels that dwarf anything our Sun has ever experienced. This gravitational compression will trigger hydrogen fusion in a spherical shell surrounding the inert core, but this shell burning will be unlike the controlled nuclear reactions that have characterized our Sun's main sequence lifetime. The energy production will be erratic and intense, generating more power than the current Sun while operating in a much smaller volume. The excess energy will have nowhere to go but outward, pushing against the overlying stellar material with a force that will fundamentally alter our star's structure. Our Sun will begin to swell. The transformation from yellow dwarf to red giant will unfold over roughly 100 million years, a cosmic instant compared to the billions of years of stable main sequence burning, but still a time span that encompasses the entire history of complex life on Earth. As the Sun's outer layers expand outward, driven by the intense energy production in the hydrogen-burning shell, the surface temperature will drop from the familiar 5,800 Kelvin to perhaps 3,500 Kelvin, giving our star the deep red colour that characterises these stellar monsters. But the cooler surface temperature is deceiving. Despite the red giant Sun's cooler exterior, its total energy output will increase dramatically as its surface area expands exponentially. At the peak of the red giant phase, our Sun may shine with 2,000 times its current luminosity, turning the inner solar system into a furnace that will make the surface of Mercury today seem pleasantly cool by comparison. The scale of this expansion defies comprehension. Our Sun, currently a modest sphere 1.4 million kilometers in diameter, will grow to perhaps 300 million kilometers across, large enough to engulf the orbits of Mercury, Venus, and possibly Earth itself. To visualize this transformation, imagine Earth's orbit as the size of a basketball court. The current Sun would be smaller than a marble at centre court. The red giant Sun would fill the entire gymnasium. Mercury will be the first victim of this stellar metamorphosis. As our Sun's outer atmosphere expands beyond Mercury's orbit, the innermost planet will find itself ploughing through increasingly dense stellar material. The atmospheric drag will cause Mercury's orbital velocity to decay, sending the planet spiralling inward toward the stellar core. Within perhaps a few million years, Mercury will disappear entirely, its rocky material vaporized and incorporated into the expanding solar atmosphere. The planet's death will not be quiet. As Mercury spirals deeper into the red giant's extended atmosphere, tidal forces will stretch and deform the planet, generating enormous amounts of heat through friction and gravitational flexing. The surface will melt and then vaporize, creating a trail of rocky vapor that will be swept up by the stellar winds. For a brief period, Mercury's vaporized remains will create spectacular streamers and jets visible in the red giant's outer atmosphere before being dispersed and incorporated into the stellar material. Venus will follow a similar fate, though its larger mass and greater distance from the Sun will allow it to survive slightly longer. As the red giant's atmosphere expands to encompass Venus's orbit, the second planet will experience surface temperatures that will vaporize even the refractory metals in its crust. The thick carbon dioxide atmosphere that currently makes Venus a hell world will be stripped away entirely by the intense stellar winds, followed by the gradual erosion of the planet's rocky surface. The fate that awaits Venus offers a preview of the forces that will reshape the entire inner solar system. The red giant Sun will generate stellar winds far more powerful than anything our current star produces, with velocities reaching thousands of kilometers per second, and carrying away perhaps 30% of the Sun's total mass over the course of the red giant phase. These winds will be dense enough to create significant atmospheric drag on any surviving planets, gradually spiraling them inward toward destruction. Earth's destiny during the red giant phase remains one of the most actively debated questions in stellar evolution. Computer simulations produce conflicting results, depending on the precise assumptions about solar mass loss, atmospheric drag, and tidal interactions. Some models suggest that our planet will be engulfed and vaporized like Mercury and Venus, its rocky material joining the expanding stellar envelope. Other calculations indicate that Earth might migrate outward as the Sun loses mass, potentially surviving the red giant expansion at the cost of being transformed into a molten airless rock orbiting within the atmosphere of a dying star. The most optimistic scenarios for Earth's physical survival offer little comfort for any hypothetical life forms. Even if our planet escapes direct engulfment, it will experience surface temperatures exceeding 1,500 degrees Celsius, hot enough to melt copper and turn the solid crust into oceans of lava. Any remaining atmosphere will be stripped away by the intense stellar winds and radiation, while the magnetic field that has protected Earth for billions of years will likely be disrupted by the extreme conditions. The geological processes that have shaped Earth's surface throughout its history will be overwhelmed by the scale of heating during the red giant phase. Volcanic activity will become continuous and global as the crust softens and loses its structural integrity. The tectonic plates that currently drift across Earth's surface at rates measured in centimeters per year will accelerate dramatically, possibly breaking apart entirely as the underlying mantle becomes superheated and turbulent. The oceans, long since boiled away during the earlier phases of solar brightening, will exist only as trace amounts of water vapor in the stellar atmosphere. But even these molecular remnants will not survive the intense ultraviolet radiation from the nearby stellar surface, which will photodissociate water molecules and allow the hydrogen to escape to interstellar space. By the end of the red giant phase, Earth will be completely desiccated, with no trace remaining of the water that once filled ocean basins and supported the emergence of life. Mars, currently a cold, dry world with a thin atmosphere, will experience a brief renaissance during the early stages of the red giant expansion. As solar luminosity increases by orders of magnitude, the frozen carbon dioxide at Mars's polar ice caps will sublimate, thickening the Martian atmosphere and potentially warming the planet enough to support liquid water on its surface. Ancient riverbeds that have been dry for billions of years may flow again, and the subsurface permafrost that contains vast amounts of frozen water may melt and create temporary lakes and seas. This Martian renaissance will be short-lived, however. As the red giant continues to expand and intensify, Mars will eventually suffer the same fate as the inner planets, with its atmosphere stripped away and its surface heated beyond the melting point of rock. But for perhaps a few 100 million years, Mars may represent the final refuge for any life that manages to survive the Sun's transformation, a temporary oasis in a solar system being consumed by stellar fire. The asteroid belt, that collection of rocky debris between Mars and Jupiter that represents the building blocks of a planet that never formed, will be completely disrupted during the red giant phase. The intense radiation and stellar winds will gradually erode the smaller asteroids, while the larger bodies will be perturbed out of their current orbits by the changing gravitational field as the Sun loses mass. Some asteroids will be flung into the outer solar system or ejected entirely, while others will spiral inward to join the vaporized remains of the terrestrial planets. Ceres, the largest object in the asteroid belt and technically a dwarf planet, contains significant amounts of water ice beneath its rocky surface. During the red giant phase, this ice will sublimate and create a temporary atmosphere and possibly even surface water, making Ceres briefly habitable before it too succumbs to the overwhelming heat and radiation. The irony is profound. Worlds that were too cold and distant to support life during the Sun's main sequence. Lifetime will have brief moments of habitability just as our star begins its death throes. The transformation of the Sun into a red giant will also have dramatic effects on the outer solar system, though these changes will be less immediately destructive than the incineration of the inner planets. Jupiter, Saturn, Uranus and Neptune will experience significantly increased heating as solar luminosity increases by orders of magnitude, causing their atmospheres to expand and their chemical compositions to change as previously frozen compounds vaporize and undergo photochemical reactions. The moons of the giant planets will face the most dramatic transformations. Europa, with its subsurface ocean currently locked beneath kilometers of ice, will experience complete melting of its icy shell, potentially creating a global ocean on its surface for the first time in its history. Enceladus, Titan, Ganymede and Callisto will undergo similar transformations, with their icy surfaces melting and creating temporary atmospheres rich in water vapor and organic compounds. Titan, Saturn's largest moon, will experience perhaps the most spectacular changes. Its current thick atmosphere of nitrogen and methane will be supplemented by water vapor as surface ice melts, creating a complex atmospheric chemistry that could produce a rich variety of organic compounds. The methane lakes that currently dot Titan's surface will evaporate, while new bodies of liquid water may form as the temperature rises. For a brief period in cosmic terms, Titan may become one of the most Earth-like worlds in the solar system, with a substantial atmosphere, liquid water on its surface, and complex organic chemistry. But like Mars, these transformations will be temporary. As the red giant phase progresses and solar radiation continues to intensify, even the outer moons will become too hot to maintain stable atmospheres or surface liquids. The water that briefly flowed on their surfaces will be photodissociated and lost to space, leaving behind desiccated worlds orbiting in the expanded atmosphere of a dying star. The gravitational effects of the red giant transformation will be as significant as the thermal effects. As the Sun loses perhaps 30% of its mass through stellar winds, the gravitational binding of the entire solar system will weaken. All planets will migrate to larger orbits as the reduced solar mass loosens its gravitational grip. But this orbital expansion will not necessarily save them from the other destructive effects of the red giant phase. The complex gravitational interactions between the migrating planets may also lead to orbital instabilities that could eject some worlds from the solar system entirely. Computer simulations suggest that the outer planets may survive the red giant phase, but in significantly altered orbits that bear little resemblance to the current neat arrangement of planetary distances. The precise gravitational architecture that has maintained stability in our solar system for billions of years will be permanently disrupted. As the red giant phase reaches its climax, our Sun will begin experiencing thermal pulses, periodic episodes of instability in the nuclear burning shells that will cause dramatic variations in luminosity and mass loss. During these pulses, which occur roughly every 100,000 years, the Sun may brighten by factors of thousands and eject enormous amounts of material into space. Each pulse will be visible from thousands of light years away, creating a beacon that announces the death throes of our solar system to any observers elsewhere in the galaxy. The final thermal pulse will mark the beginning of the end of the red giant phase. The outer layers of the Sun, loosened by billions of years of stellar winds and made unstable by the chaotic energy production in the nuclear burning shells, will be expelled entirely into space. This mass ejection will occur over perhaps 100,000 years, creating an expanding shell of glowing gas that will become a planetary nebula, one of those beautiful ghostly structures that astronomers observe throughout the galaxy as monuments to stellar death. Yet even if Earth somehow survives the red giant phase intact, an even stranger fate awaits in the cosmic aftermath, when our Sun contracts into a white-hot ember that will illuminate the remains of our solar system with alien light for billions of years to come. In the aftermath of our Sun's violent transformation from red giant to white dwarf, a ghostly silence will descend upon what remains of our solar system. Where once a bloated stellar monster filled the inner system with its extended atmosphere, now only a white-hot ember the size of Earth will remain, glowing with surface temperatures exceeding 100,000 Kelvin, 20 times hotter than our current Sun's surface. This stellar remnant will contain roughly half the mass of the original Sun compressed into a sphere small enough to fit within the boundaries of our planet, creating gravitational fields so intense that atoms themselves are crushed into new configurations of matter. The white dwarf will be surrounded by one of the most beautiful and haunting structures in the cosmos, a planetary nebula formed from the expelled outer layers of the dying red giant. This expanding shell of ionized gas will glow with ethereal colors as ultraviolet radiation from the hot white dwarf core excites the scattered atoms, creating intricate patterns of emission that will be visible from thousands of light years away. For roughly 100,000 years, our former solar system will be transformed into a cosmic lighthouse, its death throes illuminating nearby regions of the galaxy with the scattered remnants of planets, moons, and the star that once nurtured life. But as the planetary nebula gradually expands and fades, dispersing its material into the interstellar medium, a new and alien solar system will begin to emerge from the ashes of the old. The white dwarf, though only a fraction of its former size, will continue to radiate enormous amounts of energy, not from nuclear fusion, which ended with the ejection of the outer stellar layers, but from the gradual release of thermal energy stored in its incredibly dense interior. This cooling process will take trillions of years, creating a stable energy source that will far outlast the main sequence lifetime of ordinary stars. The radiation environment around a white dwarf represents something entirely alien to our experience of stellar illumination. Unlike our current Sun, which emits most of its energy in the familiar visible light spectrum, the newly formed white dwarf will radiate primarily in the ultraviolet and X-ray portions of the electromagnetic spectrum. The intense high-energy radiation will ionize any remaining atmospheric gases and break apart complex molecules, creating a harsh environment that would be instantly lethal to any form of life as we know it. Yet as the white dwarf gradually cools over millions of years, its surface temperature will drop, and its radiation will shift toward longer wavelengths. Eventually, the stellar remnant will emit most of its energy in visible light, creating the possibility for a new habitable zone much closer to the star than anything in our current solar system. This zone of potential habitability will lie roughly where Mercury orbits today, perhaps 50 million kilometers from the white dwarf, close enough that any surviving worlds will be tidally locked, with one hemisphere permanently facing the star while the other remains in eternal darkness. The concept of life around a white dwarf was once considered pure science fiction, but recent astronomical observations have revealed that such systems may be more common than previously imagined. In 2019, astronomers detected water vapor in the atmosphere of a planet orbiting a white dwarf star located 80 light-years from Earth, providing the first direct evidence that worlds can survive their star's transformation and potentially maintain conditions suitable for life. The discovery suggests that the violent death of a star need not mark the end of planetary evolution, but might instead represent a new beginning under alien conditions. The planets that might exist in this post-red giant solar system would bear little resemblance to the worlds we know today. If Earth somehow survived the red giant phase, a possibility that remains hotly debated among astronomers. It would be a fundamentally transformed world. The intense heating during the stellar expansion would have melted and resurfaced the entire planet, erasing every trace of its biological and geological history. Continental drift would have accelerated to rates measured in meters per year rather than centimeters, completely rearranging the surface features and potentially creating entirely new ocean basins as the crust cooled and contracted. The atmosphere that eventually formed on this transformed Earth would be utterly alien. The original nitrogen-oxygen atmosphere that supported life for billions of years would have been stripped away during the red giant phase, replaced by an atmosphere composed of whatever gases could be outgassed from the molten crust during cooling. This might include water vapor from subsurface ice that somehow survived the intense heating, carbon dioxide from carbonate rocks broken down by extreme temperatures, and various trace gases that would create atmospheric chemistry unlike anything in our current experience. More intriguingly, the gravitational disruption during the red giant phase might have captured new worlds into the white dwarf system. Planets from the outer solar system, originally orbiting far beyond Neptune, could have migrated inward as the Sun lost mass and the overall gravitational architecture of the system evolved. These worlds, composed largely of ice and rock, might find themselves in the white dwarf's habitable zone after billions of years in the frozen outer darkness. Consider the fate of Europa, Jupiter's ice-covered moon that currently harbours a subsurface ocean beneath its frozen shell. If Europa were somehow transported to the white dwarf habitable zone, perhaps through a complex series of gravitational interactions during the red giant phase, the intense radiation would initially sterilize its surface and strip away any atmosphere. But as the white dwarf cooled and the radiation environment became less hostile, Europa's ice would begin to melt, potentially creating the first surface ocean in the Moon's history. The tidal forces from the nearby white dwarf would be extraordinary, far exceeding anything Europa experiences in its current orbit around Jupiter. These tidal stresses would generate internal heat through friction and flexing, potentially maintaining geological activity that could replenish atmospheric gases and provide energy sources for primitive life. The day-night cycle would be eternal rather than periodic. The side facing the white dwarf would experience continuous illumination and heating, while the far side would remain in permanent cold and darkness. Such a world would create environmental gradients unlike anything in our current solar system. The day side might maintain liquid water at temperatures suitable for life, while the night side could retain frozen reservoirs of water ice and other volatiles. The terminator zone, the boundary between the illuminated and dark hemispheres, could become a region of extraordinary complexity, with temperature gradients driving atmospheric circulation patterns that transport heat and moisture between the two extremes. The chemistry of such worlds would be dominated by the unique radiation environment of the white dwarf. High-energy photons would drive photochemical reactions that could produce complex organic compounds from simple atmospheric gases, potentially creating the building blocks for biological evolution. The lack of a thick atmosphere to filter ultraviolet radiation would be challenging for surface life, but subsurface environments or regions shaded by topographic features might provide refuges where biological processes could develop. Recent computer models of white dwarf planetary systems have revealed that stable, long-term habitability is indeed possible under the right conditions. Unlike main sequence stars that gradually brighten and eventually exhaust their nuclear fuel, white dwarfs provide remarkably constant energy output over timescales that dwarf the entire history of life on Earth. A white dwarf with a surface temperature of 5,000 Kelvin, similar to our current Sun, could maintain that temperature for more than 100 billion years, providing stable conditions for biological evolution far longer than any main sequence star. The longevity of white dwarf illumination raises profound questions about the long-term evolution of life in the universe. While main sequence stars like our Sun provide stable energy for roughly 10 billion years, white dwarfs could theoretically support biological evolution for trillions of years. If life can adapt to the unique conditions around these stellar remnants, white dwarf systems might represent the future of biological complexity in an aging universe where main sequence stars are becoming increasingly rare. The discovery of planetary systems around white dwarfs has revolutionized our understanding of stellar death and planetary survival. One particular white dwarf system hosts a planet roughly 7 times the size of Earth in a tight orbit that takes just 34 hours to complete. Despite the intense gravitational field and radiation environment, this world has maintained a substantial atmosphere and shows evidence of complex atmospheric chemistry. Other white dwarf systems show evidence of rocky planets, asteroid belts, and complex debris structures that suggest dynamic planetary evolution continuing long after stellar death. These observations provide crucial insights into what might await our own solar system in its post-red giant future. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will likely survive the red giant phase, though in altered orbits and with dramatically changed atmospheric compositions. As these worlds migrate inward during the white dwarf cooling phase, some of their moons might find themselves in the new habitable zone, creating opportunities for surface liquid water and potentially even biological evolution. Titan, Saturn's largest moon, presents perhaps the most intriguing possibility for post-red giant habitability. Currently shrouded in a thick nitrogen atmosphere with methane lakes dotting its surface, Titan contains vast amounts of organic compounds that could serve as the raw materials for biological chemistry. If Titan were transported to the white dwarf habitable zone, its atmospheric chemistry would be completely transformed by the intense ultraviolet radiation, potentially creating conditions more suitable for water-based life than the current methane-based chemistry. The subsurface oceans that currently exist beneath the icy shells of Europa, Enceladus, and other outer moons could be exposed to direct stellar radiation for the first time in their history. These oceans, which have been isolated from surface conditions for billions of years, might harbour primitive life forms that could adapt to the new radiation environment and potentially colonise the surface of these transformed worlds. But perhaps the most remarkable aspect of white dwarf planetary systems is their potential for hosting multiple generations of life. Unlike main sequence stellar evolution, which follows a predictable path toward red giant expansion and planetary destruction, white dwarf systems could experience cycles of habitability as new worlds migrate into the habitable zone over cosmic time. A white dwarf system might host life on one world for billions of years, then see that world migrate out of the habitable zone as orbital evolution continues, only to have a new world arrive and begin its own biological evolution. The implications for astrobiology are staggering. In a universe where most stars will eventually become white dwarfs, these systems may represent the primary venues for biological evolution in the distant cosmic future. While young, hot stars continue to form in star-forming regions throughout the galaxy, the majority of stellar mass is already locked up in long-lived red dwarf stars and the remnants of stellar death. White dwarf systems, with their potential for trillion-year habitability, may be where consciousness and complexity ultimately flourish in an aging cosmos. The search for life around white dwarfs has become one of the most exciting frontiers in modern astronomy. The James Webb Space Telescope and other advanced instruments are beginning to probe the atmospheres of planets in these systems, looking for biosignatures and signs of atmospheric chemistry that could indicate biological processes. The discovery of oxygen, water vapor, or other compounds associated with life in a white dwarf planetary atmosphere would revolutionize our understanding of how and where life can emerge and persist in the universe. As we contemplate the possibility of life flourishing around the white dwarf remnant of our own sun, we must confront the profound temporal scales involved. The white dwarf cooling process occurs over trillions of years, timescales so vast that they encompass the entire future evolution of the universe as we know it. Any life that emerges around our sun's white dwarf remnant would have more time for biological evolution than has elapsed since the Big Bang itself. The creatures that might eventually inhabit these twilight worlds would be the products of evolutionary pressures utterly unlike anything that shaped life on Earth. Adapted to eternal day-night cycles, extreme tidal forces and radiation environments that shift gradually over millions of years, they would represent forms of biological organization that we can barely imagine. Yet they would also be the inheritors of a solar system that once nurtured the only known example of consciousness in the universe, carrying forward the possibility that intelligence might once again emerge from the ashes of stellar death. As we trace these cosmic possibilities into the deep future, we must confront the unsettling evidence that similar endings have already begun elsewhere in our galaxy, and that the cycle of stellar death and potential rebirth is one of the most common processes shaping the evolution of worlds throughout the cosmos. 7,000 light-years from Earth, in the constellation Aquarius, a ghostly eye stares back at us across the cosmic void. The Helix Nebula, often called the Eye of God, spans nearly 3 light-years in diameter, a colossal bubble of glowing gas expanding outward from a white dwarf star at its centre. The intricate structure reveals itself in layers of ethereal beauty, delicate filaments of ionized hydrogen glowing red, oxygen emissions painting blue-green highlights, and countless knots of denser material streaming away from the central star like tears frozen in time. This is not merely a beautiful astronomical object captured by our telescopes. This is a funeral shroud, the final exhalation of a star almost identical to our Sun, a cosmic monument marking the death of a world system that once might have harboured planets, moons, and perhaps even life. When we observe the Helix Nebula through our most powerful instruments, we are looking directly at our own solar system's destiny, gazing across space and time at the fate that awaits every sun-like star in the galaxy. The central white dwarf, now barely visible as a dim point of light amidst the glowing nebula, was once a yellow star much like our Sun. For billions of years it burned hydrogen in its core, providing steady illumination to whatever worlds might have orbited within its gravitational embrace. But roughly 10,000 years ago, that star exhausted its nuclear fuel and began the violent transformation we have traced in our own Sun's future, the expansion into a red giant, the ejection of its outer layers, and the final collapse into a white dwarf remnant. The expanding shell of gas that creates the nebula's spectacular appearance consists of the star's former outer atmosphere, expelled during the final red giant phases and now illuminated by ultraviolet radiation from the hot white dwarf core. Mixed within this glowing shroud are the ashes of stellar nucleosynthesis, carbon and oxygen forged during helium burning, nitrogen created through complex nuclear processes, and trace amounts of heavier elements that were synthesized in the star's interior over billions of years. These scattered elements represent more than mere stellar debris. They are the raw materials for future generations of stars and planets, the cosmic inheritance that dying stars bequeath to the galaxy. When the Helix Nebula eventually fades and disperses its material into the surrounding interstellar medium, those enriched gases will be incorporated into new star-forming regions, potentially giving birth to planetary systems with rocky worlds capable of supporting complex chemistry and life. This cycle of stellar death and cosmic recycling has been operating throughout the galaxy's 13.6 billion-year history, gradually enriching the universe with the heavy elements essential for planet formation and biological evolution. The iron in our blood, the calcium in our bones, the oxygen we breathe. All of these elements were forged in the nuclear furnaces of stars that died long before our solar system formed. We are, quite literally, made of stardust scattered by the death throes of countless stellar generations. Throughout our galaxy, this same drama of stellar death is playing out on thousands of stages simultaneously. Every clear night, amateur astronomers can observe planetary nebulae through modest telescopes, each one representing the death of another sun-like star. The Ring Nebula in Lyra, the Cat's Eye Nebula in Draco, the Dumbbell Nebula in Vulpecula. These familiar deep sky objects are all cosmic graveyards, the beautiful remnants of stellar systems that completed their evolutionary journey from birth to death. Recent surveys with space-based telescopes have revealed that planetary nebulae display an extraordinary diversity of shapes and structures, each one telling a unique story of stellar death. Some form simple spherical shells expanding uniformly in all directions. Others develop complex bipolar structures with jets of material streaming from opposite poles of the dying star. Still others show intricate rings, knots, and filaments that speak to the chaotic final phases of stellar evolution. The variety in planetary nebula morphology reflects the complex physical processes that govern stellar death. The rotation of the dying star, the presence of binary companions, magnetic fields, and the density structure of the circumstellar material all influence how the final mass ejection unfolds. In some cases, the central star expels its outer layers in multiple episodes, creating nested shells of material expanding at different velocities. In others, focused jets of material create hourglass or butterfly-shaped structures that can extend for light years from the central white dwarf. Perhaps the most remarkable aspect of these stellar death monuments is their transient nature. Planetary nebulae represent relatively brief phases in stellar evolution, typically lasting only 50,000 to 100,000 years, before the expanding gas becomes too diffuse to glow visibly. The white dwarf continues to cool and fade, while the nebular material disperses into the general interstellar medium, leaving behind only the stellar remnant as evidence of the system that once existed. This ephemeral quality makes our observations of planetary nebulae all the more precious. When we photograph these objects, we are capturing stellar death in the act, frozen moments in cosmic time that reveal the final transformation of stars like our Sun. The Stingray Nebula, the youngest known planetary nebula, has formed within just the past few decades, allowing astronomers to observe the transition from red giant to white dwarf in real time as the central star rapidly heats up and begins ionizing its expelled atmosphere. The implications extend far beyond the aesthetic beauty of these cosmic sculptures. Planetary nebulae serve as crucial laboratories for understanding stellar evolution, nucleosynthesis, and the chemical enrichment of the galaxy. By analyzing the spectral lines emitted by the glowing gas, astronomers can determine the precise abundances of different elements and trace how stellar nuclear processes have altered the composition of the expelled material. These observations reveal that Sun-like stars are remarkably efficient factories for producing the elements essential for rocky planet formation and biological chemistry. A typical planetary nebula contains roughly 20% carbon and oxygen by mass, along with smaller but significant quantities of nitrogen, neon, and other elements that barely existed when the first generation of stars formed in the early universe. Each dying star adds to the galaxy's inventory of heavy elements, gradually transforming the cosmos from a hydrogen-helium-dominated environment into one rich enough in complex chemistry to support worlds like Earth. The white dwarfs left behind by these stellar deaths continue their own evolutionary journey over timescales that dwarf the entire history of the universe. Initially blazing with surface temperatures exceeding 100,000 Kelvin, these stellar remnants gradually cool over trillions of years, slowly fading from white-hot to yellow to red to brown as they radiate away their stored thermal energy. The oldest white dwarfs in our galaxy, formed from the first generation of intermediate mass stars to complete their evolution, are now cool enough that their surfaces approach the temperature of boiling water. These ancient white dwarfs provide crucial insights into the early history of our galaxy and the timeline of stellar evolution. By measuring the temperatures and ages of the oldest white dwarf populations, astronomers can constrain when the first generations of Sun-like stars formed and died, providing an independent check on models of galactic chemical evolution and star formation history. But perhaps the most profound implication of white dwarf studies concerns the ultimate fate of stellar remnants over cosmic time. Unlike main sequence stars that eventually exhaust their nuclear fuel and die, white dwarfs represent the final evolutionary endpoint for the majority of stars in the universe. These stellar cinders will continue cooling for hundreds of trillions of years, eventually reaching thermal equilibrium with the cosmic background radiation and becoming invisible black dwarfs, cold, dark objects that will persist long after the last main sequence stars have burned out. The discovery of planets around white dwarfs has added new complexity to our understanding of stellar death and its aftermath. These worlds, somehow surviving the violent red giant phase of their parent stars, provide tantalizing glimpses of how planetary systems might evolve in the post-main sequence universe. Some show evidence of atmospheric stripping and surface heating that speaks to the trauma of stellar transformation. Others appear relatively pristine, suggesting that planets at appropriate distances can indeed survive stellar death and potentially maintain habitable conditions around their white dwarf hosts. The existence of these survivor worlds raises profound questions about the long-term evolution of life in the universe. If planets can survive stellar death and potentially support biological evolution around white dwarfs for trillions of years, then the majority of life in the cosmos may exist not around main sequence stars like our Sun, but around the cooling remnants of stellar death. The universe's biological future may belong to organisms adapted to the alien conditions of white dwarf planetary systems. Recent computer simulations have explored how planetary systems might evolve during and after stellar death, revealing complex dynamics that can scatter some worlds to interstellar space, while delivering others into potentially habitable orbits around white dwarfs. The gravitational chaos of the red giant phase acts as a cosmic lottery, randomly determining which worlds are destroyed, which are ejected, and which are repositioned for potential habitability in the post-main sequence era. These models suggest that our own solar system's transformation will likely scatter the outer planets into new orbital configurations, with some potentially migrating inward to the white dwarf habitable zone. Jupiter's moons, Europa, Ganymede, Io, and Callisto, might find themselves in direct sunlight for the first time in their history, their icy surfaces melting to reveal subsurface oceans and potentially creating conditions suitable for biological evolution. The chemical composition of white dwarf atmospheres provides additional insights into planetary survival and destruction. Many white dwarfs show evidence of heavy element pollution, traces of silicon, magnesium, iron, and other rocky planet constituents that have been accreted from disrupted planetary material. These observations suggest that not all planets survive stellar death intact. Some are torn apart by tidal forces or gravitational interactions, their remains eventually spiraling into the white dwarf and contaminating its pristine hydrogen-helium atmosphere. The pattern of heavy element pollution in white dwarf atmospheres tells a story of systematic planetary destruction, with smaller rocky worlds being disrupted while larger, more distant planets survive. This process of selective planetary survival may be common throughout the galaxy, creating white dwarf systems populated by the remnants of former gas giant moons, while the original terrestrial planets are reduced to trace elements in the stellar atmosphere. As we survey the galaxy's population of white dwarfs and planetary nebulae, we are essentially conducting a census of stellar death, cataloguing the end products of billions of years of stellar evolution and the transformation of hydrogen-rich primordial material into the complex chemical inventory that makes rocky planets and biological chemistry possible. Each planetary nebula represents not just the death of a star, but the birth of new possibilities for future generations of worlds. The beauty we observe in these cosmic monuments to stellar death reflects more than mere aesthetic appreciation. It represents the universe's capacity for transformation and renewal, the process by which stellar death becomes the foundation for new birth. The elements scattered by dying stars will eventually be incorporated into new stellar nurseries, where gravity will once again gather cosmic gas and dust into protostars that will begin their own nuclear burning and illuminate new families of worlds. This cycle of death and renewal has been operating since the first massive stars began dying in the early universe, gradually transforming the cosmos from a simple hydrogen-helium mixture into the chemically rich environment we observe today. The process will continue as long as stars continue to form and die, with each generation of stellar death enriching the galactic medium and enabling more complex chemistry in subsequent generations of planetary systems. But perhaps the most unsettling realization emerging from our study of stellar death throughout the galaxy is how this cosmic process shapes not just the formation of elements and planets, but the very possibility for consciousness to emerge and contemplate its own existence in a universe where every star must eventually face the same inexorable fate. In the constellation Cygnus, 2,000 light-years from Earth, a red dwarf star no larger than Jupiter continues its patient nuclear burning, converting hydrogen to helium at rates so slow that it will maintain this stellar fire for more than 1 trillion years. This ancient star, born when our galaxy was young and destined to outlive virtually every other object in the visible universe, represents the ultimate victor in the cosmic struggle between stellar death and stellar longevity. While our sun races toward its red giant transformation in a mere 5 billion years, this humble red dwarf will continue shining long after the last white dwarfs have cooled to invisibility and the universe itself has expanded into a cold, dark realm where new star formation has ceased entirely. The profound disparity in stellar lifetimes forces us to confront a disturbing truth about our place in cosmic history. We exist during what astronomers call the Stelliferous Era, a relatively brief period in the universe's evolution, when conditions are optimal for star formation and planetary evolution. This golden age of stellar activity, which began roughly 100 million years after the Big Bang and will continue for perhaps another 1 trillion years, represents less than 1% of the universe's ultimate timeline. We are living during the cosmic equivalent of a brilliant summer morning, unaware that an endless winter awaits. The red dwarf stars that will inherit the universe possess lifetimes so extraordinary that they challenge our understanding of what permanence means on cosmic scales. A red dwarf with half the mass of our Sun will burn steadily for over 100 trillion years, a span of time so vast that it encompasses more than 7,000 times the current age of the universe. During this inconceivable duration, these stars will provide stable energy sources for any worlds fortunate enough to orbit within their narrow habitable zones, creating opportunities for biological evolution that dwarf anything possible around more massive stars. Yet even these stellar titans cannot burn forever. The fundamental laws of thermodynamics ensure that every nuclear furnace will eventually exhaust its fuel and fade into darkness. When the last red dwarf finally dies, perhaps 100 trillion years from now, the universe will enter the degenerate era, a dark age dominated by white dwarfs, brown dwarfs, and the cold remnants of stellar death. No new stars will form, as the universe's expansion will have dispersed the gas clouds necessary for stellar birth beyond the reach of gravitational collapse. This timeline of cosmic evolution places our Sun's death in a sobering perspective. The violent transformation that awaits our solar system represents just one of countless stellar deaths that will occur during the universe's brief flowering of stellar activity. Yet for all its cosmic insignificance, the death of our particular star carries unique weight as the termination of the only known cradle of consciousness in the universe, the end of a 4.6 billion year experiment in planetary evolution that culminated in minds capable of contemplating their own cosmic context. The question of whether consciousness can survive the death of its parent star represents one of the most profound challenges facing any hypothetical technological civilization. Unlike the gradual environmental changes that have shaped biological evolution on Earth, stellar death occurs on timescales that compress the entire history of complex life into what amounts to cosmic moments. Any species hoping to survive their star's transformation must achieve technological capabilities that seem almost godlike by current human standards. The options available to a civilization facing stellar death are limited and extraordinary. They might attempt to migrate to other star systems, though the vast distances between stars make interstellar colonization a task that would require technologies and social structures far beyond anything we can currently envision. Alternatively, they might try to modify their planet's orbit or atmospheric composition to survive the changing stellar environment, essentially terraforming their world to match new stellar conditions. Most ambitiously, they might attempt to intervene in stellar evolution itself, removing mass from their aging star to extend its main sequence lifetime or artificially triggering the helium flash to stabilize nuclear burning. Recent advances in our understanding of stellar physics have revealed that such stellar engineering might not be entirely impossible, though it would require energy expenditures comparable to the entire output of a star over geological time. A sufficiently advanced civilization might construct vast arrays of mirrors or other devices to redirect stellar radiation, effectively controlling the energy balance that determines stellar structure. They might harvest material from the stellar atmosphere to reduce the star's mass and extend its lifetime, or inject new hydrogen fuel into the stellar core to restart nuclear fusion after it begins to fail. But even these seemingly impossible technologies represent only temporary solutions to the fundamental problem of cosmic mortality. No amount of stellar engineering can prevent the eventual heat death of the universe, the final state of maximum entropy, when all energy has been dispersed and no further work can be performed. The universe itself has a finite lifetime for supporting complexity and consciousness, measured in eons that make stellar death seem like a brief interruption. The recognition of universal mortality transforms our perspective on the significance of consciousness in the cosmos. If intelligence represents the universe's attempt to understand itself, the mechanism by which cosmic evolution becomes self-aware, then the preservation and propagation of consciousness takes on moral weight that transcends the survival of any individual species or civilization. We become not merely biological entities struggling for survival, but carriers of the universe's capacity for self-reflection, temporarily embodying the cosmos's ability to contemplate its own existence and ultimate fate. This cosmic perspective reveals the profound responsibility that consciousness bears in an ultimately mortal universe. Every scientific discovery that advances our understanding of cosmic evolution every work of art that captures the beauty and meaning of existence, every act of love and compassion that acknowledges the preciousness of conscious experience. All of these represent consciousness fulfilling its cosmic function of bearing witness to the universe's brief flowering of complexity and beauty. The search for extraterrestrial intelligence takes on new urgency when viewed against the backdrop of universal mortality. If consciousness is indeed rare in the cosmos, then every instance of intelligent life represents an irreplaceable perspective on the universe's self-understanding. The loss of any conscious species, whether through stellar death, environmental catastrophe, or technological failure, diminishes the universe's capacity to know itself and reduces the total sum of cosmic self-awareness. Recent theoretical work in astrobiology has explored the possibility that advanced civilizations might develop strategies for preserving consciousness across cosmic timescales that dwarf stellar lifetimes. Digital consciousness transfer, hibernation through stellar death phases, or migration to increasingly long-lived energy sources might allow intelligence to persist through multiple cycles of stellar birth and death. The most speculative scenarios envision civilizations that learn to extract energy from black holes, proton decay, or even the quantum fluctuations of empty space, creating technological civilizations that persist long after all stars have died. Yet these possibilities, however fascinating, cannot escape the fundamental constraints imposed by the laws of physics. The second law of thermodynamics ensures that entropy always increases in closed systems, leading inevitably to the heat-death scenario where all energy becomes evenly distributed and no further work can be performed. Even if consciousness somehow survives the death of all stars, it must eventually succumb to the universe's approach to maximum entropy. The timeline of this universal death is almost incomprehensibly vast. Current estimates suggest that protons themselves may decay after 10 to the 34th power years, dissolving even the atomic nuclei that comprise ordinary matter. Black holes will gradually evaporate through Hawking radiation over timescales measured in 10 to the 67th power years for stellar mass black holes and up to 10 to the 100th power years for the supermassive black holes at galactic centers. After this ultimate evaporation, the universe will consist only of elementary particles and photons, dispersed across vast distances by cosmic expansion and approaching absolute zero temperature. These numbers are so large that they defy intuitive understanding. The heat death of the universe will occur at a time when the current age of the cosmos, 13.8 billion years, becomes an infinitesimally small fraction of total elapsed time. Every star that has ever shone, every planet that has ever formed, every thought that has ever been thought, will be separated from the final state of the universe by temporal gulfs that make geological time look instantaneous. In this context, the death of our sun becomes simultaneously insignificant and profoundly meaningful. Insignificant because it represents merely one stellar death among countless billions that will occur during the universe's brief stellar phase. Meaningful because it marks the end of the only known instance of consciousness in the cosmos, the termination of a unique perspective on cosmic evolution that may never be replicated elsewhere. The possibility that Earth hosts the universe's only conscious observers adds existential weight to every moment of our existence. If consciousness is indeed a rare cosmic phenomenon, then every human lifetime represents a precious opportunity for the universe to experience itself subjectively, to appreciate beauty, to grapple with meaning, and to bear witness to the extraordinary cosmic story that has unfolded since the Big Bang. This realization transforms the way we understand both individual mortality and species survival. Death becomes not merely the end of biological function, but the termination of a unique cosmic perspective, the silencing of one voice in what may be a very small chorus of conscious observers. The survival of our species and the preservation of human knowledge and culture become cosmic imperatives, ways of ensuring that the universe's capacity for self-understanding persists as long as physically possible. The technologies we develop to extend human lifespan, the efforts we make to preserve human knowledge, the energy we invest in spreading life to other worlds, all of these activities take on cosmic significance when viewed as attempts to maximize the universe's total conscious experience before the inevitable heat death brings all awareness to an end. Yet perhaps the most profound implication of cosmic mortality is not the urgency it creates for survival, but the meaning it gives to the time we have. In a universe where consciousness is temporary and rare, every moment of awareness becomes infinitely precious. Every sunset witnessed, every scientific insight gained, every act of love expressed represents the universe briefly awakening to its own beauty and meaning through conscious minds that emerge from stellar nuclear fusion and will return to cosmic dust. The final night on Earth, when it comes, will mark more than the end of our planet or the termination of human civilization. It will represent the closing of a chapter in cosmic evolution, the moment when one particular arrangement of matter and energy that had achieved the remarkable feat of self-awareness returns to the unconscious processes of physics and chemistry. The atoms that once comprised human brains will be scattered through space, perhaps eventually incorporated into new stars and planets, where the cycle of cosmic evolution might begin again. But the universe that emerges from our sun's death will be fundamentally different from the one that gave birth to consciousness on Earth. The story that began with stellar nucleosynthesis, creating the heavy elements necessary for rocky planets and biological chemistry, will have been told, its pages written in the neural networks of human minds and the cultural achievements of human civilization. Whether that story will ever be read again by other conscious minds in other parts of the cosmos remains one of the deepest mysteries of existence. Standing beneath our sun's familiar light, knowing what we now know about the timeline of stellar death and cosmic evolution, we confront the ultimate questions that consciousness poses for itself. What does it mean to be aware in a universe that will eventually become unconscious? How should we live with the knowledge that every star will die and every mind will be silenced? What obligations do we bear as potentially rare carriers of cosmic self-awareness? The answers to these questions cannot be found in the physics of stellar evolution or the mathematics of cosmic expansion. They emerge from the mysterious fact that the universe has somehow arranged itself into patterns complex enough to contemplate their own existence and ultimate fate. In the brief span between the birth and death of stars, consciousness has emerged to witness the cosmos and find it beautiful, meaningful, and worthy of preservation for as long as the laws of physics allow. In a universe where every star must die and every world must end, what does it mean to call any night our final night? Perhaps it means recognizing that every night is precious, precisely because it is temporary, every moment of consciousness valuable because it represents the universe's fleeting opportunity to know and appreciate itself through minds that are themselves made of stellar ashes contemplating their cosmic origins and inevitable return to the darkness between the stars. The final night on Earth, when it comes, will also be the universe's final night of knowing itself through human consciousness. Unless we find ways to carry that light to other worlds, other stars, and other chapters in the cosmic story that continues to unfold in the vast darkness of space and time,